Good day, my name is Yabjani, matrix number 207158. I'm from Group 7, which is Linde Technology with the feed as coal and the production of 550 tons of ammonia per year. Okay, thank you.
Hi, my name is Aizuddin Azim bin Shazlan. My matrix number is 208144 and I'm from Group 7.
Hi, my name is Nurifka binti Apri. My matrix number is 207371. I am from Group 7.
Hi, my name is Nurul Proto Ainaja binti Mafazli and my matric number is 205691 and I'm from Group 7.
Hello everyone, my name is Elvina with matrix number 206611 from Group 7.
Now I'm going to start our group presentation for ECH3114 Material Balance Project Ammonia Production by Group 7. The objective of our project is to produce 550,000 tons of ammonia from feedstock of coal by using Linde process. This is our overall unit block diagram. We have gasifier, reformer, heat temperature shift, heat exchangers, absorber, pressure swing adsorption, ammonia synthesis, distillation column, and nitrogen unit. There are 4 assumptions that we made while doing this design process. The first one is our plant design will be operated for 365 days per annum with 24 hours of working. And the second assumption is our plant design production is constant. We assume our plant design to be in continuous steady state. And the last one is our calculation for cost and profit are based on Australia coal price. Let's look into the first block, which is gasifier. So the purpose of gasifier is to change coal into syngas through combustion. Syngas contains methane, carbon dioxide, carbon monoxide, hydrogen gas. But methane is especially used to make ammonia. Gasifier requires water and oxygen within specific ratios, which the ratio of coal to water is 1 to 1.2, and the ratio for coal to oxygen is 1 to 0.94. And the gasifier operates at the temperature of 2000 degrees Celsius with a pressure of 24 bar. So the basis of our feedstock is 951.9 kilogram per hour of coal. Our coal consists of carbon, hydrogen, nitrogen, oxygen, sulfur, and water. For the 9 and 4 streams, we have oxygen and water respectively in the form of gas. As for the outlet streams, we have the unreacted carbon purged out from stream 5. And the other stream, which is stream 7, contains hydrogen gas, nitrogen gas, water, carbon dioxide, carbon monoxide, methane, carbonyl sulfide, and hydrogen sulfide, which will go to the next block, reformer.
The function of nitrogen unit is to supply nitrogen to ammonia synthesis in order to produce ammonia. The air enters nitrogen unit with temperature of -196 degrees Celsius and 1034 bar of pressure. There is no reaction involved in nitrogen unit. In the nitrogen unit, it separates oxygen and nitrogen. The oxygen gas is kept in the storage tank while nitrogen flows into the ammonia synthesis unit. Steam reforming is the reaction of methane and other higher hydrocarbons with steam in the presence of catalysts to form carbon monoxide, hydrogen, and carbon dioxide. The main purpose of this technology is to produce hydrogen. In reforming process, steam, which is water, and methane are converted into hydrogen, carbon dioxide, and carbon monoxide in the presence of nickel catalyst. Below are the reactions involved in steam reforming. The reaction is strongly endothermic, therefore heat must be used in the process. Normal steam to carbon ratio is maintained at 3 to 1. The inlet enters reformer with a temperature of 450 degrees Celsius and 24 bar of pressure. Methane reacts with steam and produces hydrogen and carbon monoxide. Later, carbon monoxide reacts with steam to produce carbon dioxide and more hydrogen. Since the reaction is endothermic, we use nickel catalyst and maintain the temperature at 850 degrees Celsius to obtain 97.1% of methane conversion and 92% of carbon monoxide selectivity.
Next is reducer process. Reducer process independently developed by Linde and Lurgi use methanol as a physical solvent to separate H2S, COS, and CO2. Low temperature and high pressure result in increasing of acid gas solubilities and selectivities in physical solvent methanol and prevent the loss of methanol. The two main sections in reducer process are sour components absorption and solvent regeneration. In our project, we use an absorber and a distillation column. Heat exchanger decrease the temperature from 480 degrees Celsius to negative 50 degrees Celsius to satisfy the operating condition for the latter unit, which is absorber. Okay, next, the absorber that function to selectively remove CO2, COS and H2S. The operating condition is at negative 25 degrees Celsius and 33 bar. Methanol acts as the solvent with absorption capacity 12250 liter per minute. We can calculate the inlet by using the ideal gas equation of state and the absorption capacity. The undissolvable gas will leave from the top while the dissolvable gas will leave from the bottom. We can calculate the mole flow rate of CO2 at the bottom by using the percent of CO2 absorbed in methanol. Then we can solve the material balance. Distillation column will then recycle back the methanol at temperature of negative 7.7572 degrees Celsius and pressure of 33 bar. To solve the material balance, we need to find the vapor pressure of carbon dioxide at negative 7.7572 by using the Antoine equation and its mole fraction by using the Henry's law. The methanol feed of the mixer can be calculated by subtracting the methanol feed of the absorber with the recycled methanol. This heat exchanger will later increase the temperature from negative 45.5 degrees Celsius to 20 degrees Celsius before entering the pressure swing absorption.
High temperature shift converter under the technology lean process. The purpose of using high temperature shift converter is to generate more hydrogen from carbon monoxide and hydrocarbon reacting with steam. It is also to convert carbon monoxide to carbon dioxide, since carbon monoxide and carbon dioxide are both poisonous gas. It is easier for us to remove carbon dioxide later on in the absorber. The fractional conversion of carbon monoxide is about 80% and the H2 recovery is about 40%. Catalysts are usually iron oxides. The temperature range from 350 to 500 degrees Celsius and the pressure is around 23 bar. So this is the process unit. We have our inlet coming in at a temperature of 830 degrees Celsius and a pressure of 35 bar. The stream 9 going out at 480 degrees Celsius and 23 bar. And we have our unknowns here. We have 8 unknowns and we have 2 reactions. We have 2 extra info. By using the fractional conversion of carbon monoxide, we can find our outlet of carbon monoxide. By using our H2 recovery, which is 0.4, we can find out our H2 at the outlet stream. Since we have 2 reactions, we can label the first one as epsilon 1 and the second one as epsilon 2. We have our 2 known values here at the outlet stream. We can find epsilon 1 and epsilon 2 just by substituting both together. So here we have the equation 1, equation 2, and then we get our 2 values. And then by substituting the values into the other 2 equations, we can find our outlet stream for H2O and also CH4. Moving on to COS balance. So we can just equate the first inlet and the outlet together, and then we can find our outlet stream for COS. Same goes for H2S balance, and then using C balance, we can find out our carbon dioxide at the outlet stream. Thank you.
Okay, so I'm going to present on PSA, pressure swing absorption, where its function is to deliver hydrogen at purity rate of 99.999%. And then one of its primary application is used in large scale to produce ammonia. Okay, the schematic drawing of PSA and the working principle of PSA. This is the overall PFD, and this is zoom in PSA in the PFD. Okay, so why we choose PSA? Because it has a high fractional conversion of hydrogen gas, which is suitable for Linde as it needs a high purity of hydrogen gas. PSA also can separate hydrogen gas from other syngas and remove other unnecessary gases as purge. So this can prevent accumulation of purge gases. Okay, so the process specification is the flow from heat exchanger flow to PSA. Then hydrogen is being purified and other syngases are removed, such as nitrogen, water, carbon monoxide, carbon dioxide, and methane. So it operates with a pressure of 20 degrees Celsius and 60 bar as a pressure. So in PSA, there's no reaction and gas separation membrane occur. So the total the mass flow rate of inlet equals to outlet. So material balance is successful. So next is the ammonia synthesis unit. So the function is to produce ammonia in a large scale. So usually ammonia is used to produce fertilizers and manufactures of explosive materials, fiber, plastic. And ammonia synthesis reactor is the heart of an ammonia production because it's very important in the production of ammonia. So this is the working principle of ammonia synthesis, where this is the equation, produce ammonia. So this is the ammonia synthesis in the PFD. So the synthesis of ammonia is an exothermic reaction, negative 92 kilojoule per mole, which involves the mixing of hydrogen and nitrogen in a ratio of 3 to 1. This is the equation of ammonia. So additionally, the process includes iron-based catalyst, temperature of 450 to 600 degrees Celsius and 100 to 250 bar as the pressure. So the 99.99 pure hydrogen gas flowed from PSA into the ammonia synthesis, and nitrogen is flowed from the nitrogen unit. So nitrogen gas is being separated from oxygen because it readily came from a nitrogen unit. So extent of reaction method is used to calculate the production of ammonia synthesis as reaction occur. So the mass flow rate of inlet is equals to outlet. So the aim to produce 550,000 tons of ammonia has been achieved after scaling has done. Okay, thank you.
Now we are going to look at cash flow analysis. These are our suppliers. For water, our supply is Syarikat Bekalan Air Selangor, Syabas, and for coal, our supply is Malaysian Coal and Minerals Corporation Sendirian Berhad. Now, our raw materials are coal, water, and oxygen. However, oxygen cost is not included as we obtain it from air. The price of coal and water is in the table. So for the price of coal on average is 269 ringgit per ton, and for water is 0.002175 ringgit per ton. The price of ammonia on average is 2,121 ringgit per ton. This is our average max profit. We are expecting a huge profit for the next 16 years, starting from the year 2020 until 2036, as shown in the graph here. And this is our average minimum profit for the next 16 years, and we are still going to have profits as shown in the graph here. And the last one will be our average mid profit, which also increases in the next 16 years, as you can see in the graph here. So that is all for our cost analysis.
In conclusion, the objective of this project is to produce ammonia by using the raw material given, which was coal, with a feed mass flow rate of 8338.644 tons per year. With a feed of 100 kmol per hour of coal and water, we managed to produce 550,000 tons of ammonia per year, and it is profitable. So some recommendations. The waste material from PSA can be recycled back into the reformer in order to increase the yield of hydrogen, and the H2S sour gas is sent to a closed plant for sulfur production without just removing them.